So the title is Gravitational Wave Research at the Center for the Gravitational-Wave Universe. And instead of stating all the details of the work, I just start with some keywords we are working on. And of course, gravitational wave is one of the most important keyword. And secondly, the multi-messenger astronomy. And thirdly, cosmology. So to some extent, these are some kind of tools for advancing our knowledge on cosmology. For the gravitational waves, there are many aspects. Although it's a relatively young subject, it's not, a lot of people are working on various aspects of gravitational waves. In our center, we are trying to understand the sources of the gravitational waves and the waveforms produced by these sources. And then from the observational data, we want to know the precision of the parameters. And we are also keen on the future detectors because right now we have detectors operating at certain limited frequency range. And as I show, there is a rich frequency ranges we can explore in the future. Multi-messenger astronomy is the multi-messenger means we want to use not only gravitational waves but also other messengers like electromagnetic radiation. Nowadays, multi-messenger means many things, including neutrinos, cosmic ray, and so on. But we are limiting ourselves to the electromagnetic and gravitational wave astronomy for the multi-messenger astronomy. So for the multi-messenger astronomy, the key instrument is 7-dimensional telescope, which will be introduced in the afternoon. And with these facilities, we want to look for electromagnetic counterpart to the gravitational wave sources. And in order to do that, we also need to advance our knowledge on the kilonova, gamma ray burst, and so on and so forth. So this will be covered intensively in the afternoon. For the cosmology, we are now having some tension in the Hubble constant, and also there is a mysterious form of energy called dark energy, and we don't know the nature of the dark energy, but we want to explore how this dark energy behaves. Oh, sorry. So general floor of our center is shown here. It's a bit busy diagram, but from the gravitational wave observations, we want to utilize binary neutron stars and neutron star black hole binaries for the multi-messenger astronomy. And for the multi-messenger astronomy, we are constructing 7DT and use 7DT to find the electromagnetic counterpart. And for details, we want to do some kind of studies to find the counterpart, and we use machine learning aided data analysis, etc. And eventually want to discover alien counterpart and do the follow-up observations. And then that allow us to do some measurement of the critical parameters like Hubble constant and the equational state of the dark energy. For the gravitational wave side, we have to understand the gravitational waves. And for that, we work on gravitational wave data analysis. Now the complication arises with the eccentricity, and also not only this type of object which accompanies with the electromagnetic radiation, there are classes of gravitational wave sources which do not emit any electromagnetic radiation, but still they can be utilized to advance our cosmological study. And generally, this part is mostly called part 1, and this is part 2. And I'm going to mostly concentrate on the part 1 this morning, and some detailed talks will follow. So let me show some gravitational wave spectrum. So like electromagnetic radiation, gravitational waves has frequency depending on the types of sources. So the electromagnetic waves typically have very high frequencies, like for the optical, it's almost 10 to the 14 to 15 hertz. But the gravitational waves, the highest frequency we have so far is around kilohertz. And from about 10 hertz to kilohertz, we have detectors in the ground. So this is the only accessible window at the moment for the gravitational wave research. Of course, there is a pulsar timing array, which started to give us some interesting results, but we are not going to talk about the pulsar timing array. But I want to extend our study a little bit further down to slightly lower frequencies, because it turned out that if we push the observational frequency a little bit lower, then we can have much richer science. And I'm going to spend some time on about this. So, so this is the typical frequency range I want to cover. Cover today's talk. Okay. But we up to now we have only ground-based detectors, and we have to understand the observational results of the ground-based detectors, and also for the time being, we have to rely on the result coming from these ground-based detectors. So these detectors, there is a network of detectors called LIGO in US, Virgo in Europe, Kagra in Japan. So these detectors have similar characteristics, both in the operational principles and the detector sensitivity. So this is the detector sensitivity measured by the range of binary neutron star observations. So this curve shows that we can detect the gravitational waves coming from the merger of binary neutron star located within 150 megaparsec. And blue is the LIGO Livingston, red is LIGO Hanford. They are similar, but still a slight difference. And I started to show this from June 2023, which is the beginning of the, actually it was May, but the beginning of the first observing run. Another important detector is Virgo. Unfortunately, Virgo was not ready until this year, so they did not join the first part of the observing run. So I'm talking about this first observing run, and we finished the 3 observing runs. And you can see that this progress by looking at these numbers. So the first observing run of LIGO had a sensitivity of about 80 megaparsec, and then increased to 100 megaparsec in the second observing run. And the third observing run, they started at 100, but gradually increased to 140 megaparsec. And the Virgo was not able to join the first observing run, but during the first observing run, we have the first historical detection of the gravitational waves called 150914. It was September in 2015. So we have, it was about 9 years ago. Then during the second observing run, Virgo joined only the late part, final part, but it also made a historically important contribution in detecting this 170817. I don't want to go through the details, but thanks to the Virgo, we were able to locate this source in the sky relatively well, and therefore the electromagnetic follow-up observation was possible, and a Korean group led by Myeong-shin also made a critical role in doing multi-messenger astronomy for this object. And third observing run, that was, I think it was just before it terminated because of the COVID, but it had a good sensitivity. Virgo contributed a lot. Kagra joined in the only later part. Then we are in the fourth observing run, as I showed here. So fourth observing run started with only two detectors in May last year, and stopped at January this year. And we had a few months of the commissioning period, and then started the second part of the fourth observing run. So we are on the second part of fourth observing run. Okay. So if you compare O3 and O4, you can see that this is a time versus number of accumulated sources. So the third observing run, you have this accumulation, but in the fourth observing run, you have also see the accumulation with different slope, which means that we have better sensitivity. And better sensitivity means more detections and further detection, further distances. So for the O3, this is the range of the sources, and the O4, you see there are sources at greater distances. Another very important factor, at least for us who are working on the gravitational wave observations, we have low retraction, which means that software became also is working much better. Some highlights of the O4 observations. So we immediately announced the significant detections. So they have some criteria. As of October 13, yesterday, it's also the same for today because there is no any other detection. So we have 149 detections, and most of them are classified as BBH. But there are a few interesting exceptions. One, this is already published, and this is a 2005-29. This is a neutron star black hole binary, but the most important part is black hole mass. Black hole is in the mass gap. Mass gap means there is a certain range of mass of the black hole where you are not supposed to have a black hole. So this is an interesting detection. We don't know how it's formed, but the discovery itself is very important. And then 230627, which means in June 27, there is an important, interesting object which is composed of neutron star and black hole binary, and 2307 also on NSBH. I distinguished between the ones upper and lower based on the sky localization, but it's also depending on when you have observed. So this is 2422 has a smaller localization area, and so on and so forth. I highlighted this one because this has been a very interesting object for the follow-up observations. So the data analysis and public alert diagram I start with this diagram. This is the time of merger. And for the case of neutron stars, actually you can detect this event is coming even before the merger, because the neutron star binary neutron stars, the signal lasts much longer than the black hole binaries. And even tens of seconds before the merger, you know that the gravitational wave is happening. So in this case, early warning alert can be sent before the merger, but only possible for the binary neutron stars. It has never happened, unfortunately. And most other detections, just after the detection, first preliminary alert is sent, and the second preliminary alert. And until this, there is no human intervention. So it's all done automatically by the software. But when this type of event happens, people gather together online, not physically, and discuss what is this, and then do some human vetting. Human vetting means to see whether this is a false kind of detection or not. And then if it's a genuine detection, you send out initial alert. Or if there is something wrong, you send out the retraction, and etc. This is the kind of timeline. So let me show the example of 240422. This, according to the data analysis pipeline, M1 is 1.18 solar mass, close to neutron star. M2 is 3.4 solar mass, again in the mass gap, but we don't know. And the localization is around 265 square degrees. And the event took place on this day. This is in UTC on 21:35, and about 1 minute later, preliminary notice automatically was sent out, and then preliminary sky map was released. And I was surprised that there is a report of first electromagnetic observation by Master SAAO robotic telescope in Russia. So they were really fast. I think it's fast because it's done automatically. Of course, it's not real detection. They attempted to look at the sky. And this is the galaxy list within the sky map, initial sky map, etc. And the circular by rapid response team that after the human vetting, it was sent out. It was a bit late compared to other typical sources, because we are supposed to send out the initial, the high profile alert within 30 minutes, but somehow this was a bit late. I was not there at that time. But then, this is Gecko 70T KMTNet observations. They started doing observations 3.5 hours later, after the first detection, but maybe about less than 2 hours after the initial alert. And this is the sky coverage by 70T shown in red and KMTNet in green. And R-band imaging, low resolution spectra, and maybe you will hear more about how 70T works. And there have been about 90 GCN reports on the electromagnetic observations. There's no detection. It was surprising because it's not that far, and you should have seen this electromagnetic radiation if there is a radiation, but somehow, as far as I know, there is no detection. But 7DT has a rich data. Maybe you can dig out the data later on. Okay, so let's move on to the tension in cosmology, because we are talking about cosmology. I'm not going to describe all the tensions. The expert is Arman Shapiro sitting there, and he knows much better. But I'm just I'm going to mention about the Hubble tension. You all know that there is a discrepancy in the measured Hubble constant from the supernova Cepheid and inferred value from the cosmic background radiation. And this discrepancy is about 3 or 4 sigma away, which means that they are really different. So what it means, failure of lambda CDM cosmology, because inferred value assumes some maybe slight variation, but mostly lambda CDM. And so if the model is wrong, certainly the inferred value is wrong. Or this measured value could be wrong. So this is Hubble tension. And then probably more important question is, what is the nature of dark energy? And everybody is curious about dark energy. And I hope that we can hear more about this question from Eric's talk right after mine. But there is an interesting work by Kilian Arman recently published in PRL. So they, either local measurement is wrong, or we need to modify physics of the early universe. That's the main conclusion. It was covered by Science News, and I don't want to read this in more detail. Anyway, so what gravitational waves, why there is anything, what is relationship between gravitational waves and cosmology? Because gravitational waves allows us to measure the distances to the sources. And this measurement does not rely on a complicated calibration process. The only assumption you have is that the general relativity is correct. And to high precision, we know that general relativity is generally good for explaining gravitational waves. Many aspects, we try to see if there is any deviation from GR, from the gravitational wave data. So far, there are some upper limits, but not really significant. So Hubble constant, measurement Hubble constant is very simple, because this is receding velocity by the distance. So all you need is to measure the velocity and distances. And velocity is relatively easy to measure, because you measure the redshift. Distance is always a big problem in astronomy. So to measure the Hubble constant, people use the distance ladder, which means that you start with a trigonometric parallaxes, and use this to measure the nearby stars, and using the nature of the nearby stars to measure the more distant objects, and so on and so forth. And this distance ladder has been applied for many types of sources. But in order to measure Hubble constant, you have to really stretch this distance ladder to big distances. And during this process, there may be some systematics. But if you use the gravitational waves, you can directly measure or calculate. This is very simple, because gravitational wave has a signal which the distant independent shape of the signal, which gives you some parameters like masses and so on. Then the amplitude is inversely proportional to the distances. So you use this measured amplitude to infer the distance. But actually there is a big range of distances, because this signal also depends sensitively on the angle between the line of sight and the orbit of the binary stars. But we don't know this so-called inclination angle or viewing angle from gravitational waves alone. So that's the source of the big uncertainty. However, this is the inclination is kind of randomly distributed, and if we have many measurements of the distances to gravitational waves, then we can reduce this statistical error significantly. But from individual sources, it's difficult. However, there is a big problem in measuring the velocity because gravitational wave does not allow you to measure the receding velocity. So we need to identify the host galaxies. But in order to identify the host galaxies, you either have to find the optical counterpart, but which is very rare. So far, out of 90 detections of gravitational waves, we have only one source which have the optical counterpart. Another way is accurate localization. If you localize the gravitational wave source within for something like a few tenths of arc second, there is only one galaxy in this range. But unfortunately, gravitational wave localization is pretty bad. This is current status of the measurement of Hubble constant. These are the this is a Planck value, and this is a supernova value. And you cannot see the range of the error from this diagram, but they are far away from compared to the errors. And this is a posterior distribution of the measured Hubble constant from the gravitational waves. And we can try many assumptions, but still it's too broad. We can reduce the errors by using some additional information, but still it's beyond the this error range so far. So it seems that the best way to reduce the error range is to increase the number of detections of this multi-messenger or host-identified sources. So let me talk about the dark sirens, because as I said, there is only very few bright sirens. Bright siren means that these gravitational waves as well as electromagnetic radiation, they are very precious, but it's very rare. So if there is a good way to identify the host galaxies of these sources, it will be very useful. Angular resolution, as I said, is not very good. But if it's good, we can get very precise information on the expansion history of the universe. And Nicholas will be giving some talks, assuming some source population and different types of detectors and so on and so forth. So this is the basics of localization, and this shows why it's so difficult to localize. The main reason is actually the frequency of the gravitational wave is relatively low, which means that you don't have very good timing resolution, and that leads us to the inaccuracies of the sky localization. So if you have more detectors, we can use them to increase the localization. But this is the work we have carried out several years ago, assuming many more detectors compared to current. So you can see LHV, JIAC means J is Japan, Kagra, I is India, A is something in Australia, C is something in China. They don't exist, but there are some discussions on the detectors, which are even more sensitive than the LIGO. But unfortunately, the general conclusion is ground BBH host identification by ground-based detectors is very challenging. But maybe there is something, some hope for the next generation detectors like Einstein telescope and Cosmic Explorer, which is not considered here. Now, as I said, if I want to push the detection detectors of the gravitational wave detectors to slightly low frequencies, and so this is the sensitivity curves of the various detectors. The rightmost part is the ground-based detector, current detectors, and the low one is source generation detector, ET, and this is a LISA, and this is pulsar timing array. So in between this range from 0.01 to around 1 hertz is called mid-frequency. And in the mid-frequency range, not so many detectors have been proposed until very recently. There's one very interesting project called DESIGO by Japanese colleagues. And if DESIGO works, actually it can revolutionize our understanding of the universe by measuring the distances to the black holes and etc. Very precisely. So that's what we have done. And if we have detectors working at low frequencies, then the gravitational wave signal stays in the band for much longer time, even 1 year. And during this long period, actually the detectors are orbiting around the Earth, and therefore their plane changes and they move relative to the source, etc. They all produce some kind of modulations, and these modulations actually the pattern of the modulation depends on the exact location of the source, and so that's a very important aspect. And so accuracies of distances and the localization be significantly improved. And so this is a simulation we have done a couple of years ago. And this is a redshift and localization confidence area, 99 confidence, and this in cubic megaparsec. So we know that the uncertainties of the sky localization and the distances, and by combining this, we can convert this into the volume. And this is a volume, kind of volume uncertainty. And we know that the galaxies are rare, and for example, if the number density is 0.01 per cubic megaparsec, this is the occupation volume in this density. And if the density is higher, and of course occupation volume decreases. So actually these densities are dependent on the limiting magnitude or limiting mass of the galaxies. So if we believe that most of the sources are coming from the massive galaxies, then we can use the low density. And if you allow them to be in even relatively low mass galaxies, you can decrease this. In any case, below this line, actually, what it means is that you can uniquely identify the host galaxy. So then you can use them to construct the Hubble diagram. It's not shown. Somehow this one, the lower part is here. I don't know why. But this limiting redshift is around 0.015. This is very big distances for the measurement of the Hubble constant. and the blue is neutron stars, and purple is black hole. So assuming that so many sources have been identified, I mean the host galaxies have been identified, we can compute the probability density of the Hubble constant, and the width decreases with the number of such events, and if the event is more than 100, actually the error is within 1%. And so that's, of course, that's very tough, and we don't have such a detector, but it's very important to push this kind of mid-band detectors, at least for the cosmology. Now, at this stage, we have to worry about the eccentricity, because the ground-based detectors become sensitive from around 30 hertz, and at that frequency, the distance between the binary distance is very, very close, and therefore they are mostly assumed to be circular. But if we start with the low frequency, we start the observation from low frequencies, there could be some eccentricities, and eccentricities can add some more complications, either a better way or worse way. The good aspects of the eccentricity is that actually the parameter estimation, the precision of the parameter estimation becomes better if you know the eccentricity, assuming that you have perfect knowledge on the waveforms. So this is the another study done assuming eccentricity, and maybe you can concentrate on this. This is how much gain we have in the localization in the sky with the eccentricity. So the red one is overall circular. So the red one is 0.1, and this blue is 0.4. So the accuracy increases at least factor of 10, or even 2 orders of magnitude, which means that there is a high chance of identifying the host galaxy if there is an eccentricity. Of course, we cannot guarantee that there are so many eccentric binaries. So as I said, we need to have a precise waveforms. If your waveform is wrong, you will have a wrong parameters. So this shows that depending on the order of post-Newtonian order, you still have some differences. You have to carefully understand, study and understand the effect of increasing the post-Newtonian order. Apparently, in the earlier part is okay, so it's mostly later part would be different. And if you have incorrect knowledge of the eccentricity, you may have systematic error. And this is the study we carried out very recently. And so these 2 diagrams show the estimated parameters of the chirp mass, assume for the 0.001 eccentricity, very low eccentric, compared with this wrong model, which is circular. So this is a very small eccentricity, but still you have a systematic error in the estimated parameters by using circular waveform. And if there is an eccentricity, there is another benefit, which means that you can observe a higher order mode, which means that we always assume the quadruple mode for the gravitational waves. That's true for the circular binaries. But if it deviates from circular orbit, then you will have a higher order mode. And the higher order mode means that you have rich feature. At the same time, you will have some gravitational wave signal in the band, which appear before the the major band comes in. And so this one shows how much gain in terms of the signal before the merger. And depending on different detectors, so this is current ground-based detectors, you don't have much gain. This is signal-to-noise ratio, and this is the critical signal-to-noise ratio for the detection. For the ET, actually you will have some accumulation of signal strength before the merger, depending on the types of the sources. For example, neutron stars, they actually give a very strong power because the duration is long. And so in short, actually, we can localize the source within 10 square degrees, 1 or 1.18 hours before the merger. So it was, I showed that in the case of binary neutron stars, you can detect the signal is coming even before the merger, but that was a matter of few seconds. But here, it's 1 hour. Of course, this is ET and next generation detectors. And I ran out of time, so if there is a gravitational lensing of the gravitational waves, actually we may be able to increase the precision of the distance estimation because the amplification. And this is the work done by Kasi people led by Arman about the possible utilization of the supernova lensing to do the cosmology. And the bottom line is since the light curves of supernova is kind of well known, we can even detect the lensed supernova just looking at the light curve because they are combination. It's may not be resolved, but they are combined together, and you can estimate this time delays, etc. That's useful. And as I said, we are interested in future detectors. This is a detector concept we have put forward a few years ago. Still, we are working on this. This is ground-based mid-frequency detector. This is not as good as DESIGO, but maybe useful if we can operate this before we put detectors in space. So this has three-dimensional structure, and the principle is that you levitate the test masses by magnetic field, and you measure the oscillation of this test masses using superconducting instrumentation. And so we can detect the intermediate mass black holes. And talking about intermediate mass black holes, also we are working on gravitational wave sources with intermediate mass black holes. And so we may be able to detect this kind of black holes. This is an interesting topic because we know that there is stellar mass black holes and supermassive black holes, but nothing in between. So the gravitational wave is a very useful tool to detect the intermediate mass black holes. And I'm not going to spend on DESI data analysis, but this is a recent paper which was accepted recently by and led by Kasi group. And bottom line is that the dark energy may not be a major energy in the redshift greater than 1. Okay, so this is a summary. So I'll read only the bottom part. Sorry. So we are working on the utilization of the gravitational waves together with the multi-messenger astronomy for advancing the cosmology. So thank you very much.